In the early 1990s, software development was severely bottlenecked by hardware fragmentation. If a team wrote a program for Windows, they had to completely rewrite and recompile that logic to make it run on Mac or Unix. James Gosling and a team of engineers set out to build a language to solve this exact bottleneck. Operating out of Sun Microsystems, they developed what would eventually become Java. Their objective was strict. A developer should be able to write an application once and run it anywhere. Traditional languages like C and C++ compile human-readable source code directly into machine code. Those instructions are permanently locked to the specific hardware architecture of the machine doing the compiling. Java introduced a critical intermediary step. Instead of compiling directly to machine code, the Java compiler, known as JVC, converts source code into an intermediate format called bytecode, stored in .class files. Because bytecode is completely isolated from physical processor instructions, Java successfully decoupled software logic from underlying hardware constraints. To write and execute this bytecode, Java relies on 3 nested layers of architecture. This diagram shows the outermost layer, the JDK, or Java Development Kit. This is the comprehensive toolkit used by programmers to build applications, containing the compiler and debugging tools. Inside the JDK sits the JRE, the Java Runtime Environment. This layer provides the standard libraries and physical environment the application needs to run. At the absolute center is the JVM, the Java Virtual Machine. This is the active execution engine. The complete lifecycle works like this. The original .java source code is first processed by the JDK's compiler. The resulting bytecode file is then passed down into the JVM. Before executing any logic, the JVM strictly verifies the bytecode. It checks for memory faults and malicious code, enforcing a rigid layer of runtime security. Once verified, the JVM acts as a real-time interpreter. It reads the platform-independent bytecode and converts it on the fly into the specific machine instructions required by the host operating system. The JVM is the crucial link in the chain. By acting as a universal translator installed on the host hardware, it physically fulfills the promise of write once, run anywhere. As applications scale up, sprawling logic becomes impossible to maintain. Java enforces a strict object-oriented programming paradigm to organize and constrain system complexity. Inheritance is the primary mechanism for logic reuse. It allows new classes to adopt the properties and behaviors of existing classes, creating clear hierarchical classifications. This models multi-level inheritance. A base class passes behaviors down to a child class, extending to a grandchild class in a direct linear sequence. By contrast, hierarchical inheritance allows multiple distinct child classes to inherit traits from a single shared parent class. This structural mapping enables polymorphism, the ability for a single method name to execute entirely different behaviors depending on context. At compile time, Java executes method overloading. The compiler determines which version of a method to run simply by analyzing the number or data types of the parameters passed into it. At runtime, Java relies on method overriding. This occurs when a subclass intercepts a command and provides its own unique implementation for a method already defined by its parent class. If that subclass still needs to access the parent class's original variables or logic, developers use the super keyword to bypass the override and communicate directly up the hierarchy. These object-oriented rules ensure that developers are forced to engineer predictable, strictly typed data structures capable of massive scale. To coordinate these objects across disparate systems, engineers rely on abstraction, hiding complex implementation details and exposing only the essential features to the rest of the application. This table compares abstraction mechanisms. An abstract class packages unimplemented alongside concrete methods. An interface defines a pure behavioral contract with public, static, final variables. Crucially, a class extends one abstract class, but implements unlimited interfaces. Abstract classes establish a foundation of shared state. Interfaces guarantee structural reliability across entirely unrelated objects. Regardless of how perfectly structured the logic is, runtime errors occur. Java mitigates these using a built-in exception handling mechanism to intercept faults before they can crash the JVM. The control flow is direct. A try block isolates the risky code. If an error is detected, execution is immediately routed to a catch block, mapped to that specific fault. A finally block then executes required cleanup logic, regardless of success or failure. While exception handling prevents crashes, The power of multithreading maximizes execution speed by splitting logic into simultaneous, parallel processes. Developers generate these parallel threads either by extending the built-in thread class or by implementing the runnable interface. The JVM strictly monitors these operations, shifting threads between 5 lifecycle states: new, runnable, running, waiting, and terminated. Exception blocks ensure the logic remains continuously stable, while thread management forces the application to fully utilize modern multi-core processing hardware. To manage active data in memory, Java relies on the collections framework, a standardized set of classes engineered to store and manipulate groups of objects. The framework is divided into 3 primary architectures. A list maintains an ordered index, a set enforces data integrity by rejecting duplicate elements, and a map stores isolated key-value pairs. Analyzing the internal mechanics of a list reveals severe performance trade-offs, specifically when choosing between an array list and a linked list. An array list is a contiguous array. Adjacent blocks allow instant calculation for fast reads, but insertion requires shifting all subsequent elements right. A linked list uses isolated nodes with directional pointers. Insertion is efficient. Simply break one connection and redraw 2 new arrows. Selecting a data structure is not a syntax preference. Developers must deliberately match the mechanical properties of a collection to the exact read or write demands of the application. In-memory collections are wiped when an application closes. To persist data to external files, Java utilizes byte streams for raw binary data and character streams for encoded text. To integrate with complex relational databases, Java applications utilize JDBC, Java Database Connectivity. This API provides the required protocols to execute SQL operations. This diagram illustrates the connection pipeline. The Java application sends its commands directly to the standard JDBC API layer. The API routes those instructions down to the driver manager. The driver manager routes the command to the specific JDBC driver, which finally interacts with the physical database. There are 4 types of JDBC drivers, but Type 4, the thin or pure Java driver, is the modern standard for direct, efficient connections. Engineers establish this connection in 3 exact steps: importing the java.sql package, registering the driver, and calling the getConnection method to establish the handshake. Once the connection is live, the application creates a statement, executes the SQL query, processes rows using a result set, and securely closes the resources. By bridging the platform-independent JVM with strictly enforced object-oriented logic, optimized collections, and robust JDBC database pipelines, Java serves as a comprehensive, scalable blueprint for enterprise engineering.